have a data set. You have explored it. You have found missing values, strange values, categorical columns, and outliers. But there is a problem. You still can't simply give this raw data to most machine learning algorithms. So, what do? You pre process it. In this episode, we are going to learn exactly how an ML engineer takes messy, raw data and transforms it into something a machine learning model can actually learn from. Imagine giving a machine learning algorithm a data set containing missing values. Text like Bangalore and Mumbai, salaries ranging from 20,000 to 20 lakh, and a few completely incorrect records. The algorithm doesn't know what to do with all of this automatically. This is where pre-processing becomes critical. Data pre-processing is the process of transforming raw data into a clean and useful representation that can be consumed by a machine learning model. It can involve cleaning the data, handling missing values, encoding categorical variables, scaling numerical features, transforming variables, and creating a reproducible pre-processing pipeline. Let's take a simple example. We have age, city, income, and churn. Age has a missing value. City is text. Churn is also represented as text. A traditional ML algorithm generally expects numerical representations, so we need to transform this data. A typical pre-processing workflow might look something like this. First, we clean the data, then we deal with missing values, we encode categorical variables, we scale or transform numerical variables when necessary. We may also create new features. Finally, we have data that is ready to be used by the model. Let's start with basic data cleaning. Cleaning means identifying records that are incorrect, inconsistent, or unusable. For example, an age of -5 doesn't make sense. A date stored in 5 different formats can create problems. And duplicate records can cause the model to see the same observation multiple times. One important point: don't assume that every unusual value is an error. You need to understand the domain. An age of 250 is almost certainly wrong, but an unusually high transaction amount might actually be legitimate. So, pre processing should be based on evidence and domain understanding. Next, duplicates. Suppose customer 103 appears twice with exactly the same information. These are accidental duplicates. Keeping them could give those observations extra weight during training. But again, duplicates are not always wrong. In transaction data, for example, multiple rows for the same customer may represent completely different transactions. Now we come to one of the most common pre-processing problems: missing values. We already identified missing values during EDA. Now we need to decide what to actually do with them. The simplest option is to remove rows containing missing values. This can work when only a very small percentage of observations are affected. But if 30% of your data set is missing income, deleting all those rows could throw away a huge amount of useful information. Another approach is imputation. Instead of deleting the missing value, we replace it with a reasonable estimate. For numerical data, common choices include the mean or median. Median is often useful when the data contains outliers because it is less affected by extreme values. Here is why median can sometimes be better. Imagine our values are 20, 22, 24, 25, and 500. The mean gets pulled dramatically upward by 500, but the median remains 24. So, blindly using the mean isn't always a good idea. For categorical data, one common approach is to replace missing values with the most frequent category. But this also needs to be used carefully. If the missingness itself contains information, replacing everything with the most common category could actually introduce bias. The important lesson is this: don't treat pre processing as a collection of automatic rules. Understand the data first. Ask why the value is missing and choose a strategy that makes sense from the problem. Next, we have categorical variables. Most traditional ML algorithms work with numbers. So we need to convert categories into numerical representations. One common method is one hot encoding. You might wonder, why don't we simply assign Bangalore 1, Mumbai 2, and Delhi 3? The problem is that the model may interpret those numbers as having an order. It might think Delhi is somehow greater than Mumbai, but cities don't have that numerical relationship. That's why one hot encoding is often more appropriate for normal categories. But there are cases where numerical encoding does make sense. Suppose we have basic, premium, and enterprise. There is a natural order. In such cases, ordinal encoding can be appropriate. So the encoding method depends on the meaning of the category. Another important pre-processing step is feature scaling. Imagine one feature ranges from 0 to 100, while another ranges from 0 to 1 million. Some algorithms can be heavily influenced by these differences in scale. Scaling brings numerical features into a comparable range. One common scaling technique is standardization. We transform a feature so that its mean becomes approximately 0 and its standard deviation becomes 1. The formula is x minus the mean divided by the standard deviation. You don't need to memorize this formula immediately. What's important is understanding what the transformation is doing. Another technique is min max normalization. It typically maps values into a fixed range, often 0 to 1. Again, whether you need this depends on the algorithm and the problem. And this is an important practical point. Not every machine learning algorithm needs scaling. Distance based algorithms such as KNN and K means are sensitive to scale. SVMs and many gradient based models can also benefit from scaling. Tree based models are generally much less sensitive to feature scaling. Now, what about outliers? We have several options. We can keep them if they are legitimate. We might transform the feature. We might cap extreme values, or if we know they are caused by data errors, we might remove them. There is no universal rule. For heavily skewed numerical features, transformations can sometimes help. A common example is the logarithm transformation. It compresses very large values and can make a highly skewed distribution more manageable for certain models. Pre-processing can also include feature engineering. Sometimes the raw data isn't the most useful representation. For example, instead of giving the model a date of birth and today's date separately, we could create a meaningful feature called age. Here is another example. Suppose we know the number of purchases and the number of days a customer has been active. We could create a new feature, purchase frequency. Feature engineering is about creating representations that make useful patterns easier for the model to learn. Now, here is one of the most important concepts in this entire episode. You should be very careful about when pre processing is performed. A common mistake is to pre process the entire dataset first and only then split it into training and test data. This can cause data leakage. The safer approach is to split first, then fit pre processing steps using the training data. After that, use those learned pre processing parameters to transform both the training and test data. The test set should remain unseen during the fitting process. For example, suppose you are standardizing income. You calculate the mean and standard deviation using the training data. You then use those variables to transform the test data. You don't calculate a separate mean using the test set. Otherwise, you are allowing information from the test set to influence your pre processing. And this becomes even more important in production. When new data arrives, it must go through the same pre processing logic used during training. Otherwise, the model may receive data in a completely different representation from what it learned during training. This is why production ML systems often use pre processing pipelines. Numerical features might go through missing value imputation and scaling. Categorical features might go through imputation and encoding. The outputs are then combined and passed to the model. In Python and scikit-learn, a column transformer can help us apply different preprocessing steps to different group of columns. This is extremely useful because real data sets rarely contain only one type of features. You can then combine preprocessing and the model into a single pipeline. This is powerful because the same sequence of transformations can be applied consistently during training, evaluation, and prediction. Without a pipeline, it's easy to accidentally apply steps in the wrong order or forget a transformation. A pipeline makes the process reproducible. This is one of the differences between experimenting casually with ML and building an engineering quality ML system. Here are some common mistakes: fitting the scalar on the entire dataset, encoding training and test data differently, removing too many rows because they contain missing values, automatically deleting every outlier, and forgetting that production data must go through the same preprocessing pipeline. So, this is the complete picture. We start with the raw data, we clean it, handle missing values, encode categorical variables, scale or transform numerical features when needed, engineer useful features, and finally provide the model with a reliable representation of the data. Let's put everything together using our customer churn example. Age and income are numerical, city is categorical, last login is a date. We might impute missing numerical values, encode city, scale numerical features, and transform the last login date into something like days since last activity. Now our model has much more useful inputs. This is the transformation we are trying to achieve. Raw human friendly information becomes a numerical representation that the model can process. But remember, pre processing isn't about making data look complicated. It's about representing the underlying information in a way that's useful and consistent for the model. This is another important mindset shift. Pre-processing isn't simply about cleaning data until it looks nice. An ML engineer thinks about what information the model should learn and how to represent that information without introducing leakage or destroying useful signals. If you remember 7 things from this episode, remember these: clean invalid data, handle missing values intelligently, encode categorical variables, scale when the algorithm requires it, handle outliers carefully, avoid data leakage, and whenever possible, build a reproducible pre processing pipeline. Now our ML workflow is starting to come together. First, we explore the data, then we pre process it, then we engineer useful features, and only after that do we move seriously into model training and evaluation. A powerful algorithm cannot compensate for poorly prepared input. Good pre-processing doesn't guarantee a great model, but poor pre-processing can easily ruin one. That's why data pre-processing is not just a beginner topic. It's a fundamental machine learning engineering skill. We have now taken our raw data and learned how to clean and transform it. But there is another major question. Can we create better inputs for the model ourselves? That's exactly what we will explore in next episode, feature engineering. We will learn how experienced ML engineers turn raw information into features that can make machine learning models significantly more useful. I will see you in season 1, episode 8. Thank you for watching.